Speaker of today is Cumrun Vafa from Harvard University, and he will talk about a Swampland update. Please, Cumrun.
Thank you. First of all, I'd like to thank the organizers for inviting me and hosting this wonderful conference. I think the attempt to try to connect string theory with phenomenology is a noble cause, and I think it's deeply needed, I think, at this time. I think when I gave a talk last year, the strings, actually it happens to be exactly the same day as today as last year, a year ago. I really felt that the main focus on string theory should be phenomenology. And I think it's great that with this many people here, there's this great interest, and I think we should push it to the maximum effort we can do in this direction. So I appreciate having this conference. I'm going to talk about four papers that came out recently. One of them is with Jonathan Heckman about fine-tuning and sequestering related to Swampland. The other one is already talked about, I believe, yesterday by Gary. This is related to Branes on Swampland. I'm just going to touch on some highlights that he already talked about. Then I'm going to talk briefly about another paper, which is with Dieter and with Aaron, which actually Aaron is going to cover it more thoroughly tomorrow. So again, I'm going to have very small comments about it. And then I'm going to talk about a paper which just came out a few days ago related to the connections between these Swampland ideas and cosmology. And this is a work with Pratik Agrawal and George Zovid. The other one was with Gary and with Hichio, and the other ones I already mentioned. So I could have picked one of these and just focused on this, and maybe I should have done it. But the reason I didn't do it is that the interconnectivity of these ideas, I think, is what I want to emphasize. That there are links between them, and what we really need to do in this kind of program is to try to understand what unifies them and how is a better way to look at it. Instead of having a diverse set of ideas, just kind of see the commonality. And here I would like to actually feature this, even though it looks like this different kind of topics here, I would like to draw attention to the similarities at the end, after I talk about it. Okay, so I just cover these basically some basic ingredients of these talks, these papers in these four different topics: fine-tuning and sequestering, relation between branes and studying branes in the context of Swampland, and then features of ADS. ADS has some interesting features for Swampland which has not been studied as much. So drawing attention to the fact that ADS is somewhat different from regular familiar Minkowski case. And then introduced using these Swampland ideas a new idea involving a dark matter sector which is actually fading away, and motivation coming from dark sector combined with Swampland, and see how that fits with cosmological observations and the relation to H-naught tension, which has been recently pointed out in cosmology. So first, let me talk about the fine-tuning and sequestering. So usually we say, okay, we have a field theory and we quote-unquote couple it to gravity. And so the question is, what is wrong with that? And we have basically the idea of Swampland is that a lot of things are wrong with it. In fact, almost never you can do this. So the idea that you take a quantum field theory and couple it to gravity is wrong. However, you could ask the inverse question, what kind of field theories do you get as low energy limits of gravity? That's a better posed question. That is, you take a low energy limit of a gravitational theory and ask which kind of quantum system emerge. And the prediction is that you only will get a finite number of quantum systems. So only finite quantum field theories, quote unquote, could be couplable to gravity in this sense. So I'll try to explain why. Well, first of all, this is kind of a lore that we already know and has been already said in different ways by different people. And here I would like to draw attention to what this tells us about sequestering ideas in the context of Swampland. Can you have two decoupled sectors? How much can you decouple them? How much can you fine-tune the parameters of a Lagrangian in this context? So to consider this, consider Lagrangian of a given quantum system that you want to emerge as the infrared limit. So in the infrared limit of a quantum gravitational system, you will write down an effective Lagrangian involving some operator with some coefficients. In general, you have infinitely many operators would have infinitely many coefficients that they can be. And these coefficients, as we know in string theory, actually this was one of the Swampland conjectures which we introduced with Uguri, none of the parameters in the quantum gravitational theory are arbitrary constants. They're always wave of fields. And so the question is, okay, so you have these coefficients that appear in the Lagrangians are wave of some other fields themselves, but there are only a finite number of light fields, and therefore you would expect that there are only a finite number of tunable parameters. So if you have a finite number of massless fields, then you would expect a finite number of C's that you can tune away. Therefore, almost all of these parameters are uncontrolled. In other words, whatever Lagrangian you get, if you just assume you have a finite number of fields, you're actually saying that essentially you have very little control about what theory you end up at the end. In fact, it's surprising that you might even end up with conformal theories. Because having a conformal theory means at least the coefficients involving for the relevant operators better be exactly 0. That you can do this is actually known to be possible in many cases. Namely, we do know that in the context of compact Calabi-Yau, let's say, you do get singularities which can be interpreted as conformal system in the infrared. But this also tells you that if you have a conformal field theory which has a more complicated structure, there's going to be more and more relevant operators, and therefore you cannot accommodate them because you cannot turn off many coefficients to 0, because there are always only a finite number of possible massless modes. So for a given number of supersymmetry, given number of dimension, presumably there's a finite number of upper bound about what's the massless modes. For example, in Calabi-Yau threefolds, we expect there to be upper bound, similarly for fourfolds, and so on. And therefore, we expect, at most, a finite number of relevant operators can be tuned to 0 at best. And therefore, that means if you assume that the conformal theories can be graded by the number of relevant operators, there will be only a finite number of them that will be possibly arising in a string theory. So this already leads us to the conclusion that almost all conformal field theories belong to the swampland. It's not comforting for people who study conformal field theories. But if you're interested in gravitational aspects of it, conformal field theories are very rare. So you cannot just say, oh, I take this theory and just couple it to gravity. No problem. No, there is a problem. For example, n equals to 4 Yang-Mills, beautiful theory. Very few of them are allowed to appear in string theory. So maybe up to rank 20-something can appear in string theory that we know constructions. We don't have a proof that it cannot appear in any higher ranks, but we don't have constructions which appear beyond a certain rank. So by and large, there's going to be this restriction that that these conformal theories that arise in the quantum gravitational context are really jewels in a sense. And to kind of saying a garden variety jewel doesn't make sense. That is, you cannot just say, I just start with a generic thing and I do this generic thing. It just doesn't exist. So this intuition that we have as effective field theory is flawed. And this is basically pointing out that we should not think like that. This also tells you that if you take two conformal field theories that arise, for example, as internal singularities of some internal geometries, alpha and beta, typically their operators will be somehow coupled. And at most, a finite number of them can be set to 0, but not all of them. And in fact, they will be always coupled necessarily. So you can have sequestering can only be done for some finite number of interactions, but not more than that. So generically, you cannot sequester arbitrarily. Now, since you do get sometimes two distinct conformal theories, these interactions should be such that at least for the relevant operators, for some of them can be set to 0. In fact, even for a given conformal field theory, sometimes you have enough parameters not only to set the relevant operators to 0, but also some of the irrelevant operators to 0 as well. So it's not like they have to be just a number of relevant operators, but you cannot go arbitrarily large in number. So it's always a bound. So that's basically the lesson, that you cannot get arbitrary theories. So n equals to 4 Yang-Mills with rank bigger than 22 presumably belongs to the swampland. Okay, so that was the first topic I wanted to cover, the connection between ideas having to do with sequestering and fine-tunings and swampland. The next topic I want to talk about the relation between Branes and swampland, and this is the topic that Gary already covered in detail, I understand, yesterday. But for those who weren't there, probably it wouldn't hurt reviewing some aspects of it. So if you start with one of the swampland conditions, it is that the spectrum of the theory is complete. That if you have some gauge theory, some gauge group, some maybe higher formed gauge symmetry, the spectrum of that is complete. That means all the branes of various charges appear, and therefore we can use consistency of what lives on these branes as a probe for constraining what are the allowed theories. So branes, which has to be there because of this completeness, especially if we know that they are there, for example, by BPS condition. So if you, by there I mean that they are stable. So if you have some notion about these stable branes that you can put your finger on and try to study them, then you can potentially learn something about the theory itself. So by studying the putative theory with a given brane structure, if you come up with inconsistency, then you can throw it out. So let's apply this to one branes, namely strings, which arise in theories with 1, 0 supersymmetry in 10D and 6D. So 1, 0 supersymmetry is allowed in this chiral form in 10 and 6D. In 10D, that gives you a theory with 16 supercharges, and in 6D, it gives you a theory with 8 supercharges. So let's go to 10D. Well, 10D, we know that this is the familiar story. Already we know from anomaly cancellations of Green and Schwarz that the possibilities, just based on anomaly cancellations, are that you can have either E8 cross E8, SO32, or E8 times U1 to the 248, or U1 to the 496. And these two don't appear in the theory, in string theory. Similarly, in D equal to 6, so why these don't appear was one of the conjectures we made about the Swampland originally. There was an argument for why they don't appear after our paper came out by Taylor and company. So here we give an alternative argument for why these two cases won't appear. In D equal to 6, there are, again, infinitely many consistent-looking theories with K tensors, let's say, and some gauge groups, a collection of gauge groups GI and some representations of these gauge groups. And as again, Wadi, Taylor, and his collaborators have shown, there are typically infinitely many possible consistent examples of these things. And here we see that at least some of these infinite families can be thrown out based on simple consideration related to the strings that they could support. So the anomaly cancellations involves the Green-Schwarz mechanism. And in 10D, you get an equation of the form for the H flux, H field. DH is trace of R wedge R minus trace of F wedge F. And this is deeply related to the following fact that the string itself, if you take the string which is coupled to this B mu nu, has an anomaly on it, which is cancelled by the anomaly inflow from the bulk. And from this, you can actually, from the structure of this term, you can actually deduce what is the structure of the anomaly on the string. You find that this leads to a theory which has a gravitational anomaly, which corresponds in this case to C left equal to 16 using the structure. And so for the corresponding groups, you find the level of the corresponding current algebra is 1. They're dropping the center of mass of the would-be string. So without knowing anything about the heterotic string or whatnot, just from this structure, you can deduce from this term the C left and from this term the K's, and you get this structure. So you can immediately deduce that these two theories cannot appear because the central charges of these theories is more than 16 if you have a unitary theory. Of course, if you had a non-unitary theory, you could have supported this too. But unitarity of this theory, so since the theory is unitary, the brane in it should also be unitary, and therefore the unitarity of the theory forbids these two theories to appear. So that's a simple argument. Similarly, if you go to the 6D case, you have similar formulas. So in that context, you have a charge lattice characterized by a Q, and so you have an anomaly cancellation for the gravity and the gauge group involved coming up with two vectors in the charge lattice, A and B. And if you choose a particular string corresponding to the charge class Q, you find that the central charge of that string is given by such a formula, and the level that it supports for the particular group will be given by such a formula. So there's basically, the main point is that there's a formula that you can actually use the anomalies in the bulk to compute these central charges. But the central charge and the level of the group corresponds on the string to the level of the Kac-Moody current algebra and the central charge. And for people who are as old as I am and are familiar with the early days of string theory, this was the bread and butter of us back then when we were doing string compactifications. The affine Kac-Moody algebra and unitarity representations and all that will tell you cannot get arbitrary C's and K's. There's some relation between them. So depending on what the K is, the central charge of the theory should be bigger than or equal to the central charge of the unitary representation of Kac-Moody algebra, which is given by this formula. So you can just use these to compute the central charge of just the Kac-Moody part if it's unitary. And if you find that that's bigger than the C left, then you say, sorry, that's not allowed. That's that simple. So from this simple idea, you can rule out infinitely many theories. For example, an example of the kind studied by Kumar, Morrison, and Taylor was a theory with 8K plus 9 tensors with a gauge group E8 to the K. And if K is bigger than 2, we find that they violate unitarity by arguments similar to what I just said over here. So for K less than or equal to 2, it's okay. You can just check. And indeed, K equals to 2 is realized already in the M theory setup by taking the S1 mod Z2, the Hajar-Witten construction, and then you put, in that context, if you compactify that, let's say, on K3, and you put 24 and 5 branes in the middle, that gives you a realization of the K equal to 2. So that's already realized. And so therefore, it's exactly the right boundary for it not to be realized, and you can find that boundary directly by using the unitarity of the Kac-Moody algebra. Anyhow, the idea here is that you can use simple ideas like this to bound this, and it will be interesting to see if the other theories that Watty and company have come up with can be constrained in a similar way. I guess we're going to hear about some of these theories in 40 and 60 by Watty tomorrow, so it will be interesting to see if one can actually also generally rule out theories that we do not know how to construct in string theory. So the next thing I want to talk about is the relation between ADS and the Swampland. So, I mean, you might think that ADS and Swampland are, why do we distinguish ADS? Minkowski and Swampland is already discussed. What's the big deal about ADS? It turns out ADS is very different for some of these Swampland conditions. For example, the statement that we made that there should be infinitely many massless modes, a finite number of massless modes in a string theory is incorrect for ADS. So, easy example, take ADS 7 times S4, mod out by Zn. If n is large enough, you get infinitely many SUN times SUN gauge groups in ADS 7. And so, therefore, there seems to be no bound. You can take n as large as you want. So, what is this thing about finite number of massless modes? So, there's something bizarre in the context of ADS with the Swampland, and we want to know why is it going on, what does it mean, and whether or not one can think about, does this teach us anything about the Swampland conditions? So let me go back to one of the Swampland conditions, which was the statement that there's a tower of mass. There's a tower of light mass states emerging when you go far enough in moduli in string theory, which is exponential in distance, where you use the distance in this form, in the reading off from the kinetic term of scalars, and the tower mass goes like e to the minus c times the distance in the field space. So you could naturally think about the generalized formulation of the distance conjecture. And if you take a de Sitter ADS itself, rescaling the cosmological constant is like g goes to lambda g, or e to the tau times g itself is a distance in the field space. In this case, in the external space, not the internal space. And you can generalize this distance conjecture not to just apply to internal degrees of freedom, but to the fields living in the full theory. And in that form, you come up with a bound which tells you that again, for the same tower, there should be a tower corresponding to the masses going like a power of lambda. Namely, lambda goes like e to the field, in other words, e to the distance. So therefore, lambda goes to 0 is like infinite distance in field space. So the ADS, nearly flat ADS, should be viewed as a boundary of a moduli space. It is not like, oh, you just take lambda to 0 and you just get Minkowski space. That's incorrect. ADS never becomes Minkowski space. And that's because that's infinitely far away. You get a tower, just like the usual one. You get a dual description. Now, you might say, wait, we know ADS, you can take any lambda in all these examples. What happens? Well, if you recall, there's always ADS times something else. So when you take the ADS to go to 0 lambda, that something else becomes infinitely big. So you're not getting ADS, you're not getting Minkowski in D dimension, you get Minkowski in D plus some other dimension maybe. So that's a different story. So you get a different thing emerging. So nearly flat ADS, pure ADS in the nearly flat limit belongs to the swampland by this conjecture. And in the supersymmetric case, it seems like the fact that there's a mass goes like square root of lambda is related to the conformal dual description with the statement, basically the dual to the statement that there's a tower of states with dimensions which are integrally spaced with no gap. And people have noted this no scale separation in different forms, and this is related to that no scale separation in ADS that people have already talked about. And so this is, as I just said, is related to the existence of an extra space in ADS. But one of the amazing things is, and this is pointed out by Van Riet and collaborators, is that this same conjecture is related to this de Sitter conjecture, the refined de Sitter conjecture, if you reformulate it slightly differently. So if you refine de Sitter conjecture says if the grad V is bigger than C times V, either this is true or the grad squared of V has some negative directions. But it turns out that if you square the first relation and use this as the refined de Sitter conjecture, it also applies to ADS. Well, in the ADS context, we do know that you can have a situation where grad V is 0 when V is 0. When V is not 0, but therefore this is violated. Therefore, this better be true. But this is the statement that m squared is related to lambda for the ADS. So this second condition, as Van Riet et al. Pointed out, is exactly of the same form as m going like square root of lambda. So the refined de Sitter conjecture is actually related to the second condition because the first one would be violated for ADS. So the refined de Sitter conjecture supports this distance conjecture, supports this ADS conjecture. And then what is the story about the bounded number of massless modes? Well, I told you that ADS 4 times S7 can have infinitely many massless modes. But this tells you that you should, because of this, you should never think about ADS as a space, but ADS times X. And so there is no gauge group on the full space, ADS times X. It's only on a subspace. So there's no swampland condition which tells you that you cannot have a defect or infinitely many branes of lower dimension in a bigger bulk theory of gravity with arbitrary number of massless modes. So that's not a problem, which means that we could not have had a gauge group on ADS times S7 times S4, the full theory, but on subspaces of it, you can, and that's what's happening. So that's telling you that you should not view ADS7 by itself as a space. So I would say that in this context, it has been a misnomer when people talk about ADS CFT correspondence. I think it should be called ADS X CFT correspondence. And X is crucial, otherwise it doesn't work. So X is a necessary condition for ADS CFT to work. So I would suggest using this terminology perhaps. It's ADS X CFT correspondence. I don't have a single example of an ADS CFT correspondence. Okay, finally, I want to go to the last topic, which is what I'm most excited about actually these days, and that's related to connections between string theory and observed universe, what is related to phenomenology, hopefully. And this, in this context, is related to the dark sector. So if the de Sitter swampland conjecture is correct, it forbids quasi-de Sitter. And if so, the current cosmology must be governed by a quintessence field. Even if the de Sitter swampland conjecture is false, it is certainly natural to study quintessence models regardless. So we should study quintessence model for whatever reason. But it seems variation of the quintessence field, if you try to take quintessence models, typically in these models that you can construct, would have already varied by more than one Planck unit. And therefore, you should have begun to hit the situation where you get the tower of light modes. So if you're rolling down a field, then you should get a tower of light fields. But what are these tower of light fields? Well, it's natural to suggest that the quintessence, if you have a quintessence field in cosmology, it should couple to dark sector. It cannot couple to R sector too strongly because that's already forbidden by the fifth force experiments. So therefore, it better be in the dark sector. And so therefore, these ideas suggest that the dark sector should be the harbinger of light, tower of light states. So the dark sector should already have these light states. In fact, if you think about the lightest mass modes in the dark sector behave, typically in these moduli in string theory, you have regions where it doesn't depend too crucially on the moduli of the fields, the lightest mode. But when you go to the extremes, left or right, you get a tower of light states, which grow exponentially with some other constant, let me call it C tilde. And so in other words, if you consider some number density of the dark matters, the number density don't change, but the mass densities will begin to change as you roll down phi, because the mass of the constituents of the dark sector itself is getting light. So therefore, the dark sector is already fading away, perhaps. If we have crossed this point phi naught, then the dark sector already begins to get lighter. So could it be that we already have entered this phase? Could it be that the dark sector is fading in the sense that it's getting lighter? Well, from string theory ideas, we are led to think about the potential of V as e to the minus C phi, where C is order 1 in Planck units, and again, C tilde is order 1 in Planck units. And you can just say, you know what? I'll just take this model and couple and just see whether or not how does this work with cosmology? Can I figure out what these orders C and C tilde are just by fitting to data? The good old physics way of fitting theories to data. Well, this is what you find. So if you take this model and you look at the C and a C tilde, C is the coefficient of the potential and C tilde was the rate in which the dark sector is becoming light. If you fit it, if you look at the various data sets available, like Planck, BAO, and Pantheon, you get the 1 and 2 sigma curves in this plane, which is like this. But then if you include the recent observations by the Rees et al. Group, which involves the computation of H naught, using the recent observations, you find that actually it prefers C tilde to be non-zero, significantly to be non-zero, and the central value is somewhere around 0.3. So it's interesting that the best fit picks out a fading dark matter. And you can say, well, okay, how much is that better compared, let's say, to the lambda CDM? It turns out it beats lambda CDM by about 2 sigma. So, for example, if you take C is 0.1 and C tilde is 0.3, you beat it by 1.8 sigma. Or if you take C is 0.2 and C tilde is 0.3, you get 1.6 sigma. So already it's quite remarkable that a very simple idea from string theory, namely the idea that the dark sector is already fading, is a better fit to experiments than lambda CDM. And I'm beginning to run out of time, but let me just... So this is what I just said. So that if you ask how much is the dark matter faded, you find that in this model, from z equals to 15 to now, the redshift of z equals to 15 to now, 10% of the dark matter mass has gone down. So it's still 90% there, but 10% has faded away. It actually turns out not only it improves the tension with the recent measurement of Hubble now, H naught, but also it improves the tension with what's called the sigma 8 tension, which has to do with the amplitude of fluctuation at a particular galactic scale, called S8. So if you look at, for example, the H naught tension, so this is the central value that Rees et al. Have is something around 74. The black is what lambda CDM gives you. The dashed one is that if you get the quintessence model without the fading dark matter, and this blue one is the shift that you get when you include the fading dark matter. So it shifts it towards the central value of this HCDM. So this one is like 4.5 sigma off, and this is like 3 sigma. So it's a little bit improved. Even though it doesn't fully resolve the tension with the H naught, it actually goes in the right direction. And perhaps other ingredients in the early cosmology might shift it more closer, or perhaps some experimental things would shift them closer. But at any rate, without trying to solve the H naught problem, just from the very simple consideration that you must have a tower of light state is leading already to reducing this tension is remarkable. And also with the sigma 8, so if you look at the H naught sigma 8 tension, so this is the central value which you have here, sigma 8 and H naught region. This is the best region here. The black one, the 1 and 2 sigmas of the lambda CDM, and the blue one is what our model would be giving. So it's pushing you towards the right direction. And here it's showing you the evolution of H over H naught, H over H of lambda CDM as a function of Z. So it shows that at current time, the H in our model, which is this black, which is this dark, the blue line here, not the shaded one, actually pushes you above H0 going up, so H0 is going in the right direction. So let me conclude that, so these are some of these ideas that people have considered in the context of Swampland, and they're all related, kind of. So each one of them is like, you have all the symmetries are gauged, the symmetries are complete, they are related to each other, this one gives you the other. The fact that the symmetries are gauged means that the coupling is not weak, but this is not unrelated to the weak gravity conjecture. Weak gravity conjectures are, on the other hand, related to distance conjecture and so on. And then there is the Sitter conjecture, the ADS conjecture I talked about now, and then the finiteness of the fields, and they're all related to each other. And here today I just talked about a few of these. So for example, I talked about the Sitter conjecture and the distance conjecture in the context of cosmology. I talked about the ADS conjecture, and I talked about finiteness and fine-tuning. I also talked about the relation between some of them. For example, I talked about completeness of a spectrum and finiteness. Why does it rule out some particular theories? I talked about the ADS conjecture and finiteness and relation between ADS conjecture and the distance conjecture and the relation between the Sitter conjecture and ADS conjecture. So all of them are coming together in some particular form without putting it by hand, and it would be nice to actually come up with even a better way to formulate some mega principle which all of these would follow from. And yeah, I think it would be very, I'm optimistic that there is such a way to think about them. Thank you.
Yeah, thanks a lot, Cumrun. Questions, please.
Thank you. Oops. Thank you for the talk. One key question, maybe in your quintessence, in the part on quintessence, is when does the quintessence phase start in your model? Because z equal 15 is pretty much in the past. I mean, the cosmological constant domination is much more recent than this. So,
right.
So when do you make the quintessence?
No, the quintessence begins at the very beginning, but the slope is not always c. So the slope is bigger than 1, or the 1. So early time should be of order 50 or 100 or something. And how do we know that? Well, we know it should be large because if you start with order 1, to get a small value of the cosmological constant today, it should be more rapidly going down. So e to the minus 1 times 1 Planck will just give you 1 over e. That's not too much. So you have to have something like large values. So you should start with a strong slope, and the tracking behavior will set in at the beginning. And then as you approach current time, then the c is going down. The transition region where I draw that finite is when the transition is happening, is exactly when you go from this high slope to slow slope. So in our model, we just consider a very simple model where you have a slope of the order of 50, and then going down to slope of order of c, and then that's what we fitted, and that's what I showed you.
Hi. So when you talk about this completeness conjecture or completeness assumption, is there some way of showing it, or is it something which we just have to somehow assume?
Well, people have given arguments for it. I can recall some of the arguments. The simplest arguments relates to, for example, black holes. So for large enough charge, there's a black hole, and there's no reason that the particular charged black hole doesn't exist. So we know that by arguments of Hawking, you have entropy, and therefore they should exist because there's an entropy. And since charge, let's say 10 billion and 10 billion plus 1 exist, and then therefore 10 billion plus 1 and minus 10 billion also exist, and then you put them together, then charge 1 exists. So you can actually get any charge you want using just the Hawking argument.
Yeah.
I was slightly confused about the ADS-X CFT comment.
Yes?
Isn't the ON vector model and Vasiliev theory duality an example of ADS-CFT without X?
So let's be clear. I was talking about the case where you have a finite number of modes. You can have infinitely many modes. For example, in the SYK type model and so on, you get a tower of these light modes. So that's different. If you want to have what we usually call just the ADS gravity with a tower like that, then there's no other way.
All right. I think we should continue. Last question upstairs.
Yes, in your way of constraining the 10-dimensional and 6-dimensional theories, do you have any proposal for 4 dimensions? Any bound on the rank of the gauge groups? Or so?
Actually, good that you asked. I forgot to mention Timo here and his collaborators have actually thought about 4D, more relevant to our dimension, and they have actually put using similar ideas bounds on those cases. In those cases, the bound they put was in the context of F-theory model. But it's conceivable that you can actually push it to more general things. But the idea can apply to 4D as well.
Okay, I think we should thank Cumrun again.
Thank you.